This is the first installment of inverses of functions. And so this is going to be the first time we talk about what is the inverse of a function, what does that mean? And we're going to look at what does it look like on the graph, how are they related? And so let's look at a couple of inverses we're most likely familiar with already. We have the multiplicative inverse, which means if we have a number times its reciprocal, that equals 1. Those cancel each other out. Those are inverses of one another. Additive inverse means when you add the opposite, a plus negative a, or say 7 plus negative 7, anything that'll cancel out addition, that's an additive inverse. Whenever we're solving equations, we use these all the time. A lot of times teachers will say, well, let's undo multiplication. What do? We do division. That's really what the multiplicative inverse is. To undo addition, we do subtraction. So, what we're really doing instead of subtraction is we're adding the opposite. So a function's inverse really isn't like these at all. What it means is you switch the domain and the range. That's really what the inverse of a function is. You take the domain, make it the range, take the range, and make it the domain. Just flip-flop them around. And so let's look at, we're going to look at two examples of this. We're just going to look at the graphs in this video. The next video we'll look at the equation aspect of this. So what we're going to do is we're going to graph f of x. I made a mistake here, whoopsie. This is supposed to be not h of x, this is supposed to be f of x. And so what we're going to do is we're going to plug in some values for x. So let's start with, we'll go -2, -1, 0, 1, and 2. And let's plug those in for f, or in for x, I mean. So if we do -2 squared, that's 4. 4 times a half is 2. And then 2 plus 4 is 6. Plug in -1. -1 squared is +1. Times a half is 1/2. Plus 4 is 4.5. Plug in 0. 0 squared is 0. Times 1/2 is still 0. Plus 4 is 4. And then these other two we already know, because 1 squared is 1, times a half is 1/2, so this is 4.5. Plug in 2, and you get 6. So what I'm going to do is I'm going to graph these. We've got -2 up 6, 1, 2, 3, 4, 5, 6. There we go. -1, 4.5. And 0, 4. And then the other 2 points. So here is our parabola. Right there. Okay. So we did that one in green. We'll do the other one in orange. And for the inverse, all we do is we just flip them around. So instead of, oops, I messed that up. Not -6, right? It's +6. We're just flipping the domain and range around. So -2, 6 becomes 6, -2. And instead of -1, 4.5, we've got 4.5, -1. And to make sure I don't screw any more up, I'm just going to put in what were the x's now in the y's. And then I'll write down what were the y's now in the x column. 4.5 and 6. You probably should know at this point that the inverse is not a function because we have some repeating x values there that would fail the vertical line test, and we'll see that here in a moment. So let's graph this. We've got over 6, -2, over 4.5, 1, 2, 3, 4.5, down 1, over 4, 0, 4.5, up 1, and 6, 2. So our parabola is going to look something like this. All right, let's look at another example. Before we move on to that next example, the question we're going to answer at the end of this is, so what's the relationship between these two? How can you compare the green and the orange parabolas? We're talking transformations, is it a reflection, a rotation, a translation? What's happening there? So think about that as we're doing the next one. See if you can get that answer correct. So let's do the next one. And of course, I messed this one up. I flip-flopped those evidently. So this is supposed to be h of x, not f of x. Sorry about that. Super professional. So let's do the same thing. We're going to plug in -2, -1, 0, 1, and 2 for x. And we'll plug those in. So we do the absolute value of -2, that's 2. times 2 is 4. 4 plus 3 is 7. Let's plug in negative 1. Absolute value of negative 1 is 1. Times 2 is 2. 2 plus 3 is 5. Plug in 0, we get 3. Plug in 1, we get 5. And plug in 2, we get 7. All right, and then for the inverse, we just flip-flop them around. So this becomes 7, 5, 3, 5, and 7 for our x values. And then our y values are what used to be the x values, so negative 2, negative 1, 0, 1, and 2. So let's graph them. Let's see what these look like. Negative 2 up 7, 1, 2, 3, 4, 5, 6, 7, right there. Negative 1, 5, 0, 3, 1, 5, and 2, 7. So we've got ourselves a V shape. That's what absolute value graphs tend to look like. So there's our V-shaped absolute value graph. And then let's look at h of x, or the inverse of h of x. 7, negative 2, over 7, down 2, over 5, down 1, over 3, up 0, over 5, up 1, and over 7, up 3. Did I mess that up? I sure did, didn't I? There and there. Up. I went up too far on those other points. There we go. All right. So now we've got our orange sideways V. And so let's answer that question I asked at the end of the previous example. What's the relationship? And I'm guessing most people who are watching this are saying what's obvious, that it's a 90-degree rotation. 90-degree rotation. Rotation. This green one rotates 90 degrees and ends up there. And if you said that, that's very astute of you. Unfortunately, you're wrong. And so you're hopefully thinking, why on earth am I wrong? It's not a 90-degree rotation, but it sure does look like it's a 90-degree rotation. Well, let's do this, and maybe I can convince you otherwise. Let's call this first point A. Actually, let's do this in a different color. Let's call it first point A, next point B, next point C, D, and E. Now let's label those. So we got negative 2, 7. That one's A. Negative 1, 5 is B. C would be down here at the vertex. D would be over there, and E right here. And then what we're going to do is call the other points on the inverse the same, but we'll just call them like A prime, B prime, C prime, D prime, and E prime. Okay, so let's label those. We got 7, negative 2. That's right here. This is A prime. B prime is right next to that. C prime is the vertex. D prime and E prime. Well, now it should be a little bit more obvious, because if this was a 90-degree rotation, the A would end up right on top of E prime. Well, A is supposed to land on top of A prime. So it's not a 90-degree rotation. What it is actually, it's a reflection over this diagonal line. And that diagonal line is y equals x. So if you said it's a reflection over the line y equals x, you are a genius. So reflection over y equals x. And if we look at the previous graph, it's the same thing. So if I go back to that, if I draw that diagonal line y equals x, this graph is a reflection over that line as well. So when you have two functions that are an inverse of a function and the original function, when you graph those, they are always, always, always reflected over that line y equals x, no matter what. So if you have, I'll see if I can wing it here, a smiley face, and you reflect that over this line, oh boy, that's going to be like down here or something like that. It'll look something like that. So it's just going to be a reflection over that line y equals x. These two would be inverses. Inverses, if you can read my penmanship. Cool. So that is the end of this first installment of inverses of functions, just looking at more the graphical approach.